who's a physicist. Let's see. A moment. Give me a moment. Got it. Okay. So this is from Ricardo. He's a physicist from Spain. And what he mentioned here is that if you are like kind of like a god who knows all the laws of physics, and in your mind, if you currently know all the status of this world, and nothing would be uncertain, and the future would be like the past. And so here the x-axis is the timeline, the y-axis is like your uncertainty of the world, and you keep collecting information so you know that your uncertainty about the current status of the world would be like the variability would be shrinking. And then once you get a very certain estimate of the current state of the world, and you run a model, you will know the future. But if there is some uncertainty there, you will know that maybe the future is still uncertain due to the fact that small scale errors might grow and become dominant in the far future. So this reflects a duality between state inference and state prediction. And we don't like this kind of worldview, but it's kind of like informative. And let's look at the word that we care about. So let's consider a very typical forecasting case. And here we are showing the same layout of this thing. So the x-axis is the time, and it's starting not from the present, but from some time ago when we start to collect observations to estimate the current status of the world. So we call this status assimilation. And once we gathered all this information to constrain our estimate of the current climate status, we let go of it and we estimate the far future. And in the climate science field, we divide this kind of process into several stages. The first one is called assimilation. Assimilation is a process that we keep collecting observational information to infer the current climate status. For example, when we let I will just ask a question. So what's the weather like for now? You will get no idea if you do not have any observations. But if we tell you that what date is it today, so you will know that some seasonality information. So you start from a very ignorant status that you only know the climatological variability of the weather status. And then you keep injecting some observation along the way. And gradually you will shrink your uncertainty about the current weather status until you come to a state that you believe you have gathered you have gathered enough information about what the weather status look like today. So this is called 0 hour, and then we start to do the forecast. And we know that the small scale error would grow from like very small scale at the current state to like week two to 1 year and to 1 century. For week two, we know that the anomaly correlation coefficient would drop to around 0.6. That's where we believe that there's no practical usage of deterministic forecast. So this is called weather scale. And then if we keep let the model run to evolve this uncertain state, we'll go to the S2S subsignal to signal status, where the low frequency signals would help us to constrain the variability of the possible state. And then by 1 year or 2 years, we know that the status would like the would the variance or the entropy of our estimation would be similar to the climatological probability distribution. And then if there is some external forcing, we know that this whole distribution might shift a little bit. So this is like trying to reframe the world of climate prediction, weather prediction, assimilation in the similar manner as this kind of Laplacian demon. And we know this, and we know the duality between assimilation and prediction. And we know that this is beautiful. But what we want to do is just to quantify this whole process in a very computationally efficient manner. So we come up with this formulation. What we actually did in assimilation and prediction is trying to estimate the probability of climate state given observations, given external forcing and given some prediction model. And let me clarify this. So this is the climate status, which can be very high dimensional. It's like 1 billion dimensional if we have really high resolution model, if we have really high resolution models. Before any observation coming in, we have this. And once we have some observation coming in, we know that it will shrink. And the rate of this shrinkage depends on how much observation we have in a single step and how efficient the model is. If we have really good model, we will quickly get to a status that have low variability. If we have a poor model, we know that the shrinkage would take a little bit longer. But nowadays, usually in operational forecast, it usually takes around 6 hours. And when we are doing prediction, we want to run really large ensemble simulation. We want to have the initial state, and we evolve it with some numerical models or data-driven models, and we'll have some variability here, and we have larger variability here. We go back to internal variability here, and we know that this can change. This, as I mentioned, is beautiful, it's consistent, yet it's computationally infeasible, at least before the year 2021. And what happened in year 2021? Well, something happened. That is, we do have two models, and one model is called ChatGPT, and the other is called Diffusion. So before 2021, it's called before ChatGPT, and after 2021, it's called after Diffusion. Why do I mention these two models? Because I think these two models mark a milestone in human civilization. Why would I say that? Let's consider what ChatGPT did. It's trying to mask out some token representation of language and then try to estimate the probability of these tokens of language. So it's basically trying to help us to learn the spatial pattern of a high-dimensional object. What is diffusion doing? It's trying to say that let's add different scales of noise into a high-dimensional object. And let's try to estimate what kind of noise we added to those objects. So essentially, it's trying to estimate the different spectrum, the frequency information of a high-dimensional object. So if we can learn this spatial pattern and frequency pattern of high-dimensional object in a probabilistic manner, we know how to manipulate this high-dimensional distribution in two fundamental ways. We understand the nature, so frequency and spatial domain. So if we know that, we might be able to manipulate a lot of things that we used to think that only belong to human beings, only to belong to human intelligence. And that's why I think that 2021 is a milestone in human civilization. But before that, let's talk about what is machine learning and how these two models differ from traditional supervised learning. So these two models, they are all generative models, which means that they learn high-dimensional probability distribution, and we use this probability distribution to do some probabilistic inference. So what are supervised learning? Supervised learning basically is very simple. You have paired input-output data, which can be very huge, and you develop a parameterized function to link the input to the output. For example, you have a picture of pixels, and for these pixels, you have the RGB channel of it, and you want to link each pixel to some category that it belongs to, for example, building, truck, person, wall. And here you just maximize the overall estimation accuracy of your classifier, which is parameterized by a deep neural network, which is layers and layers of transformed representations. So you know so that the model can make very good classification in some uncertain cases. So this is called classification. And you can reformulate this for doing regression tasks and doing interpolation. So these are called supervised learning. But I always believe that these things have little to do with climate science, because if we rely on supervised learning, we always need to trust the data set we prepared. But we do not have such paired data in climate science. If you trust paired data, you trust reanalysis, you will never surpass the reanalysis data set. But what is generative modeling? So the bottom several parts there, we are doing some some demonstration of what generative model is. So the left part is called domain adaptation. Actually, this is why we want to bring in RAM to learn Cinema National Lab to keep doing. That is, we have two distributions. One distribution is those like the photograph you taken by your phones, and the other one these are drawings from those famous drawers, from famous artists, and we want to change the style without changing the content. So how can we do that? Basically, we are trying to move this distribution of real-world imagery to those drawings, and we are trying to match these two distributions. So we are manipulating distributions, or we are trying to estimate the next words or next several words based on the input words here, like when you are writing an email, or we are trying to modify an existing picture or generate new pictures based on our text prompts. Those are generative models, and these models are not trained with paired data. So we just train a very huge generative model, which is a way we represent these high dimensional distributions. And during inference, we do some posterior sampling or like some kind of posterior sampling. We do need some assumptions, but we want to include information, conditioning information during inference, not during training. And those are the gift of generative modeling.
Before you,
So,
sorry. So
uh,
I missed this. So this entanglement, what do you mean by that? Is it more like feature selection and finding some sort of low dimensional representation?
it's not that disentanglement. So this the left part. We have a paper published in James called "Learning to Correct Climate Projection Biases." Let me type it here. I think I don't. Let me type it here. One moment. So learning to, and it's in James. So what it did is that we want to maintain the what is resolved by the dicot while correcting the parameterization biases. But usually we do it in like weather reforecast. We align the model state with reality, and we observe the trajectory difference between model's prediction and reality or observations. And we see that we think the difference is due to some like small scale error that are parameterized by some empirical functions, and we try to correct that. This is one way. And the other way is to run a long-term simulation. And we know that we cannot match the trajectory with reality, but we believe that the statistics created by those long-term simulations should match historical observed climate statistics. And these are two ways. But we think that maybe we should not match the sum or any statistics of the climatological distribution, but we should just match the distribution so that once we have matched the distribution, we can find a correspondent picture that while not being sampled by this artist, but it is in the underlying distribution, so we can find the correspondence there. So for example, if this is the model world, if this is the real world, you can change this model world figure into the real world figure. And you can see that, and once they do that, you can see that you are matching the climatology distribution. So that's what I thought we could improve climate models in the era of GAN. But once we have diffusion, I think we have something that is more fruitful. So we talk about probabilistic assimilation and prediction in this figure, and we think that this can solve, I think almost 90% or 99% of the problems that we care about in climate science. We care about state estimation. We care about different processes, even the very smallest scale processes and large scale processes in the weather at weather and climate scale. But we know that it is not computationally feasible before the year 2021, and now we want to make it like computationable. So what we do here is different from any other, I would say, from many other data-driven modeling practices or numerical modeling practices. So what are we doing here? Let's say that we want to come up with a computationally feasible way to quantify the probability of climate state given observations, given a model, and given external forcing. What we did here is that we first come up with a probability distribution of historical climate state. So why are we doing this? We know that climate system is a huge dynamical system. It keeps evolving to create its like phase-based distribution or its manifold that can support some invariant measurement. For example, the probability distribution of any state to take place. And this is called climatological distribution, which we talk about a lot, but we don't know how to quantify. And we have this P of climate state. For example, if it's the atmosphere is like a billion dimensional state, and we train a diffusion model to approximate this distribution. And once we have this distribution, we want to apply it for statistical inference. And how can we link time with how can we connect different time steps state? We should have a forecasting model. This forecasting model can be a numerical model, or it can be a very poor numerical model, which in this case is a pure dynamical code that resolves the geophysical fluid dynamical equations. Or it can be a data-driven model, for example, ForecastNet, Pangu Weather, GraphCast, NeuralGCM, or anything. So once we are given this state estimation model and this forecasting model, we want to accomplish the following two tasks. The first is called assimilation, which is the left panel of this subfigure A. We want to estimate the state of the climate based on partial observations that sequentially coming within a small time window. And the next is to do prediction. We want to evolve this estimated state distribution to the far future so that at weather scale, it closely follow what reality is evolving through. And at subseasonal to seasonal scale, it provides a very tight envelope of true trajectories. And at climate scale, it goes back to climate variability, and hopefully, given some external forcing, it can respond to that forcing and create some climate change signals. So how is this achieved? This is achieved via three key techniques. The first is how we train a diffusion model, and second is called inpainting. And let's say but before that, let's say, and the third one is called a stochastic differential equation editing, which Tong Yi talked about. And let's first look at the diffusion part. So how well can we train a generative model that learn climatological distribution based on like 30 or 40 years of reanalysis data? So this is what we are doing here. So we train a diffusion model, unconditional diffusion model, using snapshots of atmospheric reanalysis, spanning different pressure levels for different variables with 1 degree resolution. And once it's trained, we want to testify how well it reproduces the climatological distribution. Because it's a very hard dimensional distribution, we cannot check all the statistics, so we only look at those that we care most. For example, the mean the mean field of temperature, 2 meter temperature, the variance of it, the minimum of it is spatial pattern, and the maximum of it. And we can also see the linear structure of it by seeing the UF of it and compare to reality. And we can also see the Hartley seal, we can see the power spectrum, we can see the adjustrophic wind to geostrophic wind, which means that the results here show that we can very well reproduce the climatological distribution revealed by climate reanalysis. Here is ERE5. Which means that the PX is pretty accurate. It assigns a maximum, it assigns a good likelihood to all those existing samples. So with that, we want to achieve the first thing that is assimilation. So how do we do assimilation? So this work is done by,
But
uh-huh.
if you go back, yes, here. So two questions. One is, do you enforce anything about geostrophy, ageostrophy, or it's just like the model captures the geostrophy correctly? The other thing is, how about the tails of the distribution? Like, do you capture the tails in?
Okay. Yeah. So the first question is no, we do not encode any physical knowledge there. It just perfectly reproduces the adjustrophic wind to geostrophic wind. And the second question is, does it capture the tails? Yes. For minimum, I think it resides in the tail. For maximum, here we are showing the maximum from reanalysis and from our generation, and also from here, if you look at the very high the right part of this power spectrum plot, we see that it preserves the energy here, and we can even do it I would say almost perfectly for precipitation. For example, here for precipitation, it's very long tail distributed. We can do the mean STD, maximum, minimum, even mimicking the reanalysis precipitation or satellite precipitation. So I don't think it's a big problem for different models. We don't need to do a lot to preserve the some high level statistics.
Okay, great. Thanks.
Mhm. So once we get this proud distribution of what a state is possible and the likelihood of it, we can use it for inputting, in which case here is to inject the observational information into the state so that we can have the state that agree with those partial observations while also having their impacts being demonstrated or being revealed here. So what are we doing here? We are given this trained diffusion model during generation. We just keep replacing the unobserved, keep replacing the observed part with noisified observational information. So this is a very basic idea that is you want to have your observations uh, show their impact in your generation result. But you can have a kind of a strict Bayesian formulation of it so that so that you can it's kind of like a posterior sampling of it. Hello, great. I I see your question.
Yeah, I had a question. So sorry, could you remind me during training, what is the diffusion model denoise? Like it's denoising to what target? Are they samples from ERA 5?
Yeah, they okay. So assume that you are familiar with different model, right?
Yeah, at a high level.
So during training, so the problem set is this: we can collect all the hourly ERE5 data, right? And for the atmosphere, like those from GraphCast or from ForecastNet, and you have all those hourly snapshots of data. You shuffle it, and then you add noise to it and denoise, so that you can do a weather generator. So basically, we train a weather generator that try to yield realistic samples while the whole distribution match reanalysis.
So you mentioned a couple slides ago in making a distinction between supervised learning and generative modeling, that for supervised you have input-output pairs where they're from reanalysis and you can do better than reanalysis, right? For generative modeling, you don't have input. You're sampling from noise distribution and learning to map that some prior noise distribution to a target distribution. But if that target distribution is also era 5, aren't you also still capped by the same limitation?
The thing is that you can do some fine tuning. And for ERE5, one thing that I'm against supervised learning is that for ERE5, you inject observational information every 6 hours. So that if there is anything wrong with their assimilation scheme, you know that hour one and
Yeah.
hour zero and hour one, hour two, they are not they they are kind of influenced by by the injection of observations,
Yeah, absolutely.
and they are not they are not perfect. And by training on that like sequential information, to the best is that you can have some forecast skill gain compared to IFS, but you cannot do assimilation. You cannot do
Okay.
very good uncertainty quantification. You cannot surpass the existing numerical model by a large margin. You cannot connect weather forecast with seasonal forecast with climate simulation in a single model, just like what numerical model did. So we want to jailbreak that paradigm. And what we did here is something else. We do not we do not stress a lot on the forecasting part. But we want to say that if we have a diffusion model, if we have a very well-trained climatological distribution, which is the phase-based distribution of this dynamical system, or some invariant measurement of it, can it help us to get something more, like data assimilation, like
I see. So
intelligent
you're
forecasting
so
system?
the assumption is that while the vector field that maps one state to another in reanalysis introduces a lot of bias of the underlying model,
Yeah,
the assumption is that the climatological distribution of the states of reanalysis are still more faithful to reality.
hopefully.
Okay.
And we do have some remedy if it is not fitting so perfectly to reality.
Mhm.
And that one can be easily done in diffusion model. It can be better done in diffusion model compared to the supervised learning method.
Okay.
Yeah, that's that's the hope, and we do have some evidence supporting that assumption. But let's just keep going from here. So we have so the problem here is that once we get a state estimate, we want to inject some immediate observation to constrain the status. So what we did here is that we select 4 snapshots of reanalysis field, and we can get some free gauge observation. These dots are observational points, and we pick some out for test without inputting the observations from here. And once we inject this like around 100 gauge points into the generation process, we can generate P of state given these observations at this immediate time step. And we can generate the ensemble mean. We can compute the ensemble mean and the standard deviation of this conditional distribution or this posterior given these observations. And we can also compute the absolute error of this ensemble mean prediction, which for the last part is the difference between this one and this one. This is reanalysis. This is the ensemble mean of our estimate. And first thing we notice here is that these two, they match very well, which means that even only with these 100 gauge points, we can have very good estimate of this whole field. And the other thing we notice here is that these two figures, they correspond very well, which means that for places that we have large errors, we know that there is large variance there because we do not have enough information to constrain the whole distribution. So which means that this is a reliable ensemble prediction of this state. And also we can compute the error for the grid points that are far away from the gauge points. And by the way, regarding the assumption that we talked about earlier, we also train this using a GCM historical simulation, FGOS. It participates in the SIMP6 project, and we do not necessarily need to train it with reanalysis. We can train it using pure GCM. And also we can quantify the value of each observation in reducing the estimation error. For example, here if we are using only 3 points to estimate the status, and we can compute the ensemble error, the ensemble means error here. And if we add a single point here, a single observation here, we can reduce the error for this whole field. And it is showing how this single observation help us to reduce the ensemble estimation error. Or we can remove some observations and we see that there is an increase of this estimation uncertainty, and these are manipulated differently for different regions. But this is just a single shot estimation of the state based on a single steps observation. So this is not assimilation. Assimilation is trying to like coordinate a sequence of observation so that we can have a very small uncertainty range. So how small should it be for current ECMWF IFS forecast system? Their analysis area is around, I would say, 5 meters for Z500. So the RMSE for their analysis field, for this initial field estimation, which 0 days forecasting error, should be around 5 meter. And so how can we further improve further decrease the uncertainty in our state estimate? So what we did is very simple. It's like we have a whole ensemble of possibility given the current day's observation, and we run a forecasting model to propagate this prior distribution, to propagate this distribution to the next time step, and then we inject the next day's observation, next time steps observation. So starting from a progress from the previous day's forecast, include today's observation, we further shrink the uncertainty here, like here. So for day one, day two, day three, day four, and these different colors mark the error and variance for different regions. And here is our final result. This is reanalysis. This is IFS T0, the ensemble mean of their estimate, which means that they start from this state to make predictions. So their prediction accuracy could not surpass this. And this is their assimilation error, kind of assimilation error if we assume this is the ground truth. And here it's using some observational experiment, which means that we select some points, and these points are the weather balloons or like gauge observations where we have to have some observations. And we use the ERE5 data here as some like pseudo observation. And here it's using the real world observation there. And we can keep injecting the observations to decrease the variance of the state estimate so we can get this final state estimations mean and standard deviation, and we can calculate the error here, which is the difference from subfigure A with C, and we get G, and A with D we get H. So if there is good correspondence between the ensemble spread and ensemble error, we know that this is pretty reliable ensemble estimation of the current weather state. And how does this compare to IFS reanalysis? So if we have around 10,000 observation points, we don't need assimilation. Within one step, we get a very small ensemble variance here. And if we if we have smaller amounts of observations, we know that, yeah, we do need keep injecting some observational information here. But we have an ensemble mean error of around 3 meters, which is also better than IFS T0. So it means that we get something better than current state-of-the-art enamel data assimilation system. And here is a systematic comparison with IFS using 1 year round evaluation. If it's blue, it means that it has smaller error compared to IFS high-res analysis. If it's red, it's not so good. And we are still working on improving the estimation of humidity. And we also noticed that, yeah, in many cases, we are not using like direct observations of wind velocity, pressure, temperature, all those things. We are using satellite, so we can run a satellite observer, like radiative transfer model, and then inject this into some high resolution simulations like WOLF. And with this, we get something better than current 4D VAR and then or 3D VAR methods. And these are for the assimilation part. But once we have this very well constrained initial state estimation, we want to make predictions. How do we make predictions? And this is work from Tongyi. It's doing the so-called super ensemble weather forecast. What we did here is that we have an initial guess of the current weather status, and we know that we want to have a forecasting model that can let us know the forecasting uncertainty, which basically comes from 3 different sources. The first one is the model bias. So for different models, whether it's data-driven or numerical model, it can have some systematical bias. And the second one is called model stochasticity, which means that all models have only very limited resolution. So we want to sample some subgrid scale noise at each forecasting time step. And we do not want the model's systematic error or stochasticity to keep compounding through the forecasting period. So we want to sample these two in each forecasting step. And this is what we did here. We use the same pre-trained diffusion model, and we add some white noise to the initial state or to model's preliminary predictions, and we remove the learned noise so that even if a model's prediction does not reside on the correct manifold, we can add some noise to put them back to the manifold and remove some noise to put it back to the manifold so that ATL creates the correct envelope of all possibilities. So this is the gist of the Gen forecast, Gen EPS, and we can use this to create a perturbation to model raw predictions, and we can also use it to collect the results from different models. So these are the results, and we can now run operational 1,000 member and number forecast for typhoon trajectory, and there's a land folding of typhoon center for lead time 6 hours up to 162 hours, and we can do atmospheric and number forecasting. And here is the scale comparison. So we know that Pangu marked an error of data-driven forecasting, but for its day 10 ACC Z500 is around 0.55. And there is something better called Fuxi and Fengwu. They have like 0.66. But if we can blend all these models, even your GCM and some numerical models here, using the GenCast methodology, or using the GenEPS methodology, we can achieve around 0.7 for 10 days Z500 forecast. And also you see that because we are keep dragging the estimated state to the manifold there, we can have some kind like strong typhoon centers here compared to pure data-driven forecasting methods. And these are for the forecasting case. But we also want to have something that have higher resolution, so we did something called similar to CODIF, but we call it the wolf, and it's also trained in a supervised manner. We have a long-term simulation using wolf, and we train a high resolution simulation here. Train a high resolution probability distribution here. So it's P of X, but X is now like 3 kilometer resolution. And then we use the low resolution simulation as some conditioning information, and then denoise it with the high resolution model. We get this kind of results, pretty similar to original wolf simulation. We see that UNet GAN models, they cannot generate these high details, and it can create like 100 member ensemble forecasting to 3 kilometer resolution, hourly scale with very high accuracy. And I will quickly skip this and go back to the forecasting for a longer time domain, a longer time range. So we know.
Hi, before you add, if I can ask a question about the slide 11. So in your diffusion model, when you add noise, is the noise added to like a spherical harmonics or some low dimensional space in the grid space? Like how do you add the noise in your diffusion model?
So we basically follow the forward process here.
Okay,
So
go
so
ahead.
follow the forward process to add noise and follow the reverse process to remove noise. But in adding noise, we are actually adding Gaussian noise, right?
But
For
but
different models, okay?
is the noise added to all variables in the
All
physical
variables.
space?
Yeah, we do not do any latent diffusion
Okay.
because we think we do not we want to preserve the matter scale structure of these geophysical fluid patterns, and we do find a lot of limitations in doing latent diffusion models for geoscience applications. I know that many of us want to do some VE compression of this geofield and then do diffusion model. I think that's a waste of time.
Okay, good to know. Okay, great. Thanks.
Yeah. And then we come to a longer term forecast. So what are we doing here? We know that here we are only focusing on the so for the current version of gap, we are only predicting the atmosphere part. But we know that the predictability limit of the atmosphere can be like 2 or 3 months. I would say some people say that it's 2 weeks. It's only determined by the ACC is larger than 0.6. But we won't have seasonal forecast. We want the ocean memory or some memory from some low frequency signals to exert their impact in some longer term predictions. So what we did here is that we can run the model for 2 or 3 months, and we start the model for from each month, and we compute its 2 month lead time global ACC is here, and we compute its 3 month lead time global ACC is here. They are not good compared to ECMWF seasonal forecasting system, which are here. But we can inject the ocean memory into our model. So how did we do it? We compute the seasonal anomaly of current SST. So for example, if for this region, the seasonal average here is around 30 Celsius, and for now you observe a 31 Celsius, you know that it's 1 degree above seasonality. So you add this anomaly to the following 2 or 3 months. To the following 3 months for each day, you add this seasonal anomaly there. And you use this SST anomaly persistence prediction to constrain your atmospheric model so that you can get so you can so the influence from the SST can get can play their role in the evolution of the atmosphere. So that here is what we get. This is done by Wei Dongli and Xin Yan. I don't know if they are here. But currently, we know is working on like doing a gap version of ocean and couple it with atmosphere so that we have a more complicated ocean model, maybe more accurate, and we have more interaction between the atmosphere and ocean. And we hope that this can be far better than 0.5236, which is already far better than this one. And finally, we can run this model for 1,000 years. And there is no accumulation of error because for each time step or for several time steps, we drag the model's prediction back to the manifold, back to the climatological distribution manifold using the diffusion model. And this is the last 40 years of annual cycle, and we compute the Yari 5 size, tropical cyclone patterns, trajectories, and we compute gaps estimation, and we can also use historical SST as forcing so that we can better mimic the historical climate, but we see that there is not so much difference here. And here the SOI, Southern Oscillation Index, is a little bit different from reality because there is no dynamical ocean here. And finally, we can use projected SST as constraint for gap so that we can generate some climate change signals. And this is basically the whole idea of gap. That is, you need to have a state model and a forecasting model, which can be any model, so that you can go from an ignorant state where you know nothing except the climatological distribution. You inject observations, so you get a very confident estimate of what is possible for now, and you keep evolving it while you're using this invariant measurement to constrain your process-based model, and you get climate simulation. So with that, you thread assimilation, nowcasting, weather forecasting, S2S forecasting, and climate simulation. So how does this compare to existing models? Like I would clarify the existing data-driven model into these three categories. The first one is pure data-driven model. It's like Pangu, GraphCast, Fengwu, Fuxi, ForecastNet. I know that Pedram, you are one of the authors in ForecastNet, and also Gencast. I don't think Gencast is any different from this forecasting model. They are purely data-driven, which means that they need to have paired data, x1, x2, x3. You want to relate x2 with x1. Using some deep neural networks, you can adapt different structures like swing transformer, like graph neural network, like some conditional differential model. Conditional differential model is also to supervised learning. You can use FNO to do that. And the second one is that you do have still preserve the dynamical code that help you to do some numerical resolving of the underlying geophysical fluid dynamical equations. But you want to have some machine learning components to tackle the unresolved process. You can train it offline, which is the machine learning parameterized GCM, like the convection parameterization, like gravity wave parameterization, like turbulence parameterization, boundary layer parameterization, and you can couple this offline trained machine learning models with the dynamical code. But it has some domain shift problem, which means that during training it performs okay, but when you couple it with the dynamical code and run it, it's bad. And with that, people come up with the so-called neural GCM. They can have a dicode wrapped out by a numerical by a deep neural network, and they train it online, so it has better inductive bias about how we go from this state to the next state, and it has some parameterized process that tackle the unresolved processes. So these are the same, basically the same. They're trying to tackle the same problem. And the third one is called ARTVAC. I don't like this paper or I hate this paper because it does not quantify any uncertainty and it's using observation to observation while missing all the physical understandings. By the physical understanding, I do not mean the equations, I mean the physical variables. I think that we have already known the degree of freedom of the climate system by quantifying some physical variables there, like the temperature, wind velocity, pressure, humidity, and these seven variables are determined by the seven equations that are partially closed. But with ARTVAC, if you do not relate those observations to the states and then go from the state to the observations, you are missing the whole part of what we want in climate science. We want to know the P of the state given observations, given some process representation, given some forcings, and we want to reveal their impact at different temporal scales. So this reminds me of these things like if you seek me via appearance, seek me via voice, these are demons road, and these are opposite to the way for Taganata, which means that they are not good. They are not. I don't like this. I don't like this way of doing things. And our paper got rejected by Nature because there is a paper saying that they can do like data assimilation in here. And this is some final remarks. The first one is that there is a broad picture of what the community believes that we should apply machine learning in climate science. So that is, we do have some well-established method to estimate the resolved geophysical fluid processes, but we don't know the micro scale processes very well. We don't know the macro scale processes very well. So we use machine learning to estimate the micro scale physical processes based on some high fidelity data, like those from high resolution simulations or from observations. And also we want to extract some signal from those macro scale processes, like you try to detect and attribute climate changes, like these papers, what they did here. But I think that there is a more unified perspective here that is we are tackling climate problems. And it's a dynamical system. It has some invariant measurement. It has some statistics. And for high dimensional statistics, you should use machine learning, especially generative modeling. But this is what I used to believe. And now I believe that this can be even simpler. That is, I think everyone should know this figure. So this is the figure from CMIP 6 white paper. It tells us why CMIP is designed in that way and what we care about in climate science. So CMIP is designed that we have a DEC experiment, which is a basic experiment. It has 4 different sub experiments with different forcing scenarios, like pre-industrial run simulation of these climate models, and 1% CO2, quad CO2, and also the AMIP experiment. These are some basic experiments. And also you have historical simulations that are forced by observed forcing scenarios. And we want to understand three things. The first is called systematical bias, which means how we represent different processes in the climate system. And second is called variability and predictability. These are some statistical property or environment measurement of the climate system. And the third they call response to forcing, but I think it's like more like forcing scenario, uncertainty in forcings, because we don't know what will happen in the future. But and they do have some things here circled around these key considerations. But I think this can be simpler. That is, what we did here is that we may want to know the status of the climate given some observations, models, and forcing. And there are three uncertainties here: process error, and variability, predictability, environmental measurement, which is PX, and some forcing uncertainty. And you also have some observations help you gauge the uncertainty in model, the variability, and also help you know what kind of forcing would be good. So actually what you want to do is to know P of X given observations, given model, and given forcing. And here we are actually have done some preliminary work P of X given observation, given forcing, and given model. And we do not necessarily need to train this using reanalysis, which means that we can inject all these model simulation here, and while having these models show their impacts here. And also we can inject this forcing scenario to modulate this whole distribution. So with this, we can totally replace CMIP. And we can answer most of the questions that climate scientists want to answer because let me give one example. Why climate change is detectable from any single day of weather at weather scale? It's because that for high dimensional cases, if X is very high dimensional, the impact of F is very apparent. This is called breadth of dimensionality. So the higher the dimension is, the easier it is to tell if a sample comes from a predefined distribution. So that's why this formulation can have some computational, implementational, and scientific values. And finally, two slides. The first is all models that run some are useful, but when does usefulness emerge? So if we want to draw a horse, you see that from figure 4 to figure 5, it used to be a joke by Van Octob. Now we know that it's diffusion model. We just need to get the basic physics while having some prior knowledge learned by a generative model to implement the details. And here, if we have a QG model, we have a dicot, we have parameterization, we have more parameterization, how can we get digital twin? We can use diffusion model to achieve this. But the last part is also very tricky. That is, it takes me 4 years to paint like Raphael, but a lifetime to paint like a child from Picasso. And even if we have a digital twin, we still need to do some explanation. And I think you can do some inverse modeling using this as a pro and do some like do something like what we did here. It's called like it's like this theory this paper. I like it a lot, and I was encouraging Weidong to keep working on it. So it's how we can do some explanation in using different models, using generative model, response theory via generative score modeling. It basically tells us how we can interpret this distribution to reveal model deficiencies, to reveal the impact from external forces, to reveal the value of different observations. And with that, I would like to conclude my presentation. I know it's pretty messy, still thick from the long trip to Singapore. And with that, looking forward to your questions.
Uh, Thank you so much. This was fantastic. And I really like your simplified set of circles. And I should say that the authors of that PRL paper will speak
Mm-hmm.
in our journal club next week,
Okay.
Friday morning. So, of course, you are welcome to join if you are interested. But yeah, like Andre, Ludvio, and others will speak about, because I also think like that kind of approach is pretty nice. Uh,
Yeah.
and of course, what you do, I think it's fantastic. So, do others have any questions?
Yeah, I have a bunch of questions, but maybe other can go first if they have some. Uh,
Yeah, I have a quick question about slide 26.
Okay.
So this is extremely impressive. Certainly it's getting the mean response to temperature right, despite only being trained on what looks like historical data. I guess I know neural GCM, ACE, we've tried this as well, where we trained this on the ERA5 period from, almost
Mm-hmm.
1940 to present, and then we put it in a 2 plus CO2 and or sorry, not 2 plus CO2, but a 2K bias for SST and a 4K bias, which are pretty similar to these scenarios, and they all absolutely fail. So I'm just curious, like the distribution of and how temperature is warming and stuff, like the response is much different in the future than what is seen during this training period. How do you explain these results, I guess? What about your model is different than everything else out there?
Okay. I think this is a very good question. So first, this is the testing of the extrapolation capability of the current model, which is not guaranteed to work, but it just empirically works. And so there's one, I heard one sentence which is very good during this year's RCLR. So which means that the sentence goes like this. I think it's from Jeff Clune. So if you want your model to extrapolate very well, you just train it in all scenarios. Do not make it extrapolate, make it interpolate. So for example here, we are training it using historical ERA5 data. And I also mentioned that we do not necessarily need to train it with reanalysis because here it's like just learning the climatology distribution and the different forcing scenarios. We definitely can train it with all the semi-5 data using all the forcing scenarios. Then we are not extrapolating. Then it will definitely work. Actually, it works, and we will release that paper in the coming months. So you can train it using future forcing scenarios.
Okay,
But
so sorry, just to make sure I understand. So in this case, it has seen future scenarios and
no,
it's
no, no. In this case, it hasn't seen.
okay.
It's already working. But if it has seen it, it will work better.
Yeah, yeah, we have those results as well. I mean, if you train it on like, for example, a 2% or 1% increasing CO2 and then ask it to predict equilibrium climates and stuff, it works well. But that to me, interpolation is much different than extrapolation. I'd
Yeah.
be very curious to see if it gets the like continental amplification or if it's just getting the mean state right. So like if you put a 4 plus CO, there's not 4 plus CO2, but 4 plus SST into any climate model, and what you would expect is, the ocean surface temperature to warm by 4 degrees, but then you would get a almost 2x response over the continents. So something like an 8 plus
I,
K.
I,
So I'd be very curious to see what the distributions of these warmings look like. So just comparing your end of century to present and then seeing what
yeah,
those look like would be very interesting in this case.
I got a point, and I think Shanshan has did some preliminary examination of the extrapolation capability of it, and we do not stress a lot on this question in this paper, and I think it's worth exploring. But for future cases, you should not only include the forcing, you should also let the model know which
Yeah,
model
of
you are
course.
trying to mimic.
I certainly agree with that. I just
Yeah.
am quite impressed by these results. Yeah.
Okay. Yeah. Thank you. And I think you will have a follow-on question that is how this model differs from these things.
Yeah, because I guess everybody has tried this. So they've tried to run GraphCast Fangu in mid-century and late century, and they
Like,
fail catastrophically. And I know Neural GCM in their paper, the reviewers asked them to run it with a 2 plus K bias in the SSTs and a 4 plus K, and it works decently well for the 2K bias, but does not work at all for the 4K bias. So it
Okay.
seems that all these models can't do what that was just shown, which is really interesting.
It's due to their objective function.
Mhm.
Their objective function is always at a weather scale, right? They are trying to predict next day's weather, which for this highly chaotic system, it never guarantees that a long-term simulation of it will yield accurate statistics. So our objective function is the climatological distribution statistics. We try to have a model that can accurately yield the climatological distribution or its statistics. So that's the key difference. And that's also why I think neural GCM is a dead end.
Yeah, I mean, I kind of
It
share
can
that.
never do weather forecasting because it just makes all those subscale processes in a single neural network.
Yeah,
It's not sustainable.
I certainly agree with that last sentiment. So I guess then one quick question is, sorry, one more question for like side 25, I guess. Yeah, how exactly what is the I assume there's some auto regression in this. So you have a model that can predict, climatological distributions and stuff, and then you're conditioning this on some forcing, which I assume is incoming solar radiation, and in this case, SSTs for the bottom one. So what is
So
like so like two questions, I guess, is what is like the inference time? Because I know diffusion models are usually somewhere 20 to 25 times slower because you have to take 20 or 25 denoising steps. So I was curious what the computational budget for something like 1,000 years simulation was.
okay. So the first thing is that we need to clarify that for this part, it's just a free run without any forcing.
Mhm. Okay, no
Even
incremental,
radiating force,
not even radiative forcing.
yeah, it's just a free run.
That's very interesting that it can
Yeah,
get the annual cycle right and stuff then.
yeah. And for the second part, the computational cost is around, as you're absolutely correct, 20 times more or 20 to 50 times more compared to like the pure data-driven forecasting models.
Okay, yeah, and just I'm just curious because we've run GenCast, and I'm sure Pedram and others in this group will ask this question. Like running GenCast is a monumental task, like
Yeah,
millions
but
of GPU hours to run a
yeah,
couple of decades worth of hindcast. So what is like, so how many years of simulation can you get per day in real time, for example? That's just usually a typical method we do in climate. So like a 1 kilometer global simulation using the world's supercomputer maybe gets you 100 days of simulation per real day. So what is this, for example, like how long did it take to make this 1,000 year forecast?
we are having a time step of 1 day, so it's
Okay,
day
one.
by day forecast. And the other thing, the other good thing that I forgot to mention here is that we do not have fixed time step, right? We can inject a numerical model here. So which means that the assimilation cycle it can take place every minute. That's a better part compared to video diffusion. So for video diffusion, if you are training it with ERE5, you have a minimum time step of 1 hour. But for here, we are training a diffusion model that does not have any time element there. So you can do like 1 minute, 1 minute, 1 minute, 1 minute. You can inject all those observations. So here for 1,000 year simulation, we are using a 1 day forecasting model. So predict next day, like Pangu weather, the largest scale model. So it can predict next day and then drag it toward climatology distribution corresponding to your prediction. And then you run it. I think it takes around 365 times 1,000 time steps, and it's acceptable. I forgot how much time it takes. It's done by Shang, and I think he has left.
No, no,
Shang,
no worries at all. This was very useful. Okay. I
yeah.
think I completely understand and have some guesstimate on how long it would take. Thank you so
Mhm,
much.
Thank you.
Great.
By the way, I don't like Gencast as well. It's similar. It's supervised learning.
Yes, yes.
Um, this is great. And as Chiang said, I think we all have a lot more questions, but I think it would be great to maybe set up another meeting at some point between just a few of us to chat more. So as you probably know, like our group, we are very interested in the extreme events, like cases of that conditional probability when P is very low, even beyond what was seen in the training set. So it would be great to chat, especially with Vedang joining, to see what are the directions we can maybe pursue together and build on what you are doing here, which is, I think, really fantastic. So I have to run to another meeting in a few minutes, but if there's any last minute question anybody wants to ask. Okay. Otherwise, we'll send you an email to find a time that maybe we can chat more. I think that would be
Yeah, definitely. Yeah.
okay. Great. Thank you so much. This was fantastic.
Thank you. I'm sure we'll have more collaborations with all the students coming.
Yeah. Yeah, that would be that's very exciting for us.
Yeah, thank you for the great talk.
I have a few questions, but I guess we can chat in private. Oh, yeah.
Yeah, definitely.
Yeah, I think that would be good.
Okay.
Okay, great. Thank you so much.
Thank you. I'll see you next time. Bye-bye.